Okay, so today I would like to share with you some thoughts about risk assessment, and the title is "Where Old Meets New," or "Where New Meets Old." We have a lot of guidance across the line of how to do risk assessment, but I think there are new developments, and new developments are needed, and I would like to share those with you as well, because I think you, as the next generation of toxicologists, I think you need to know about the new developments in that field. I have 1.5 hours. I want to make it a little bit more interactive. So please don't wait with your questions until the end, right? I would like to have a discussion at the point where we discuss it, right? So if I'm talking about something, you have a question, please don't hesitate to just raise your hand or interrupt me. I'm fine with that. So maybe I can start off with introducing myself. My name is Roger Gottschalk. Roger, or Roger in French. I don't mind, both are fine. I am working at Maastricht University at the Department of Pharmacology and Toxicology, and I'm actually a genetic toxicologist by training. I also work at the Dutch Health Council, and there I work on hazard assessment in the work environment. And I hope at the end of my talk that you understand the difference between hazard assessment and risk assessment. What I will talk about in the coming 1.5 hours, maybe a little bit less, depends also on how we participate, is I would like to start, what I'm talking about is chemical risk assessment, right? So I'm not going to talk about bacteria or something like that, risk assessment from that side. It's really the chemicals that are important in this talk. And I would like to discuss with you the current process. So what do we do at the moment? But the current processes actually cost a lot of animals. So we would also like to address that by looking for alternative approaches. And since I am working on human health, I will have a little bit more focus on human risk assessment, but I will also discuss a little bit about ecotoxicology, toxicological risk assessment. Right, we have Bertrand in the back, and he is an ecotoxicologist. So if you have to add things on the ecological part, please feel free to do so. If we look at the definition of risk assessment given by the US EPA, EPA stands for the Environmental Protection Agency, it's characterization of the nature and magnitude of health risks to humans and ecological receptors from chemical contaminants that may be present in the environment. Right, so I think there are a few words in there that are quite important. It's the nature and the magnitude. I think that's two important things, because the nature is what can a compound do, and the magnitude is how potent is the compound in doing that. So these are two things we might, in risk assessment, we might have to assess. And then, of course, we have the risk assessment in humans and in ecological receptors. So environmental living beings in the environment, like animals or plants. Right. So if we talk about these two differences between these two different types of risk assessment, we have the ecological risk assessment and human risk assessment. And there's one big difference in these two, and that is because human health risk assessment is at the individual basis. Right. So we want to protect each and every individual. The ecological risk assessment is actually more on basis of the species. You want to make sure that if I have fish in a pond, I want to make sure that I have those fish in that pond also next year. If a few fish die, we don't mind, because the species will still be there, right? So we accept if some individuals in that species will die, right? In human risk assessment, we cannot do that. We don't do that, right? We cannot put a pharmaceutical drug on the market and then say, well, 100 people will die from it, but we don't mind, because we will have people next year as well, right? So that is something, there's an important difference between ecological risk assessment and human health risk assessment, right? So we, in humans, we want to protect even the most susceptible individual, Whereas in ecological systems, well, if we care about the species and not about the individual animal in that group. I think there's you can discuss about that, whether that is a good choice. But I think that's a discussion that we do not necessarily have to do today, right? Because I think that's not the purpose of this session. Okay, so if we then move, there are more differences between human risk assessment and ecological risk assessment, and that is because in ecological risk assessment, we have a lot of species, but only a limited number of endpoints. So if you look at the species, we have plants like trees, we have animals living in the air, on the ground, in the water. So we have different areas where they are located. So there might also be different types of contamination. The contamination may behave differently in those different environments, right? So what we focus on is actually not the individual animals. We focus on the community level, the population level, the organism, and sometimes we also look into sub-organism level. So we do some histology on fish or on animals, right? So, but really the biological markers that we do as in humans, it's hardly done. It's being done more and more, I have to admit, but it's in regular risk assessment, it's not really done that often. If we talk about population level, we think about the outcomes like reproduction, survival, these kinds of things, right? So we have the bigger picture, but we don't look into the individual level. So we have here on the left, we see that compounds that we are exposed to that we assess the effect of those compounds. On the right here, you see measurements like concentrations of COPEX, which COPEX means contaminants of potential ecological concern, right? Or a wildlife exposure analysis. So this is exposure assessment. I will come back to that later on. And this is more effect analysis, right? And in risk assessment, you need both. You need exposure assessment and you need effect assessment. So the data that you have in your project, what is that predominantly related to? Exposure. Yeah, okay. Exposure. So you might have to ask yourself, do we also need something of that, right? Just as a tip. If we go to human health risk assessment, it's actually opposite, right? So in the animals, we had a lot of species with a limited number of endpoints. If we look into human risk assessment, we actually have a single species, humans, but we have a lot of endpoints, right? So if we do risk assessment, we do that on all kinds of levels. We take oral toxicity because we often are exposed to a compound because we eat it or we get it or we swallow it deliberately. If we think about drugs, we have acute dermal toxicity. If you were to be exposed on the skin, skin corrosion, eye irritation, skin sensitization, etc., etc. We also look at more reproductive health, which is also what we do in animals, right? We look at whether those animals can reproduce in ecological settings. We also do that in humans, like developmental toxicity. So if the mother is exposed during pregnancy, does that affect the baby that is developing in the womb, for instance? And does that lead to neurological defects or something like that in the development? We look at germ cell mutagenicity. And with regard to mutagenicity, the germ cell is actually has a very special place because the germ cell is not only affecting one individual, but can also affect the next generation, right? So if I have a mutation in my lungs, it is affecting me as a person, but will not affect my children and my children's children. If I have a mutation in the germline, that mutation can be given to my children, and my children have that mutation in all their cells, including their own germ cells, so they can give it again to their next generation, right? So germ cell mutations are actually quite interesting, very important in health risk assessment. but we don't test it that much because it costs a lot of animals usually, and therefore we simply don't do it. We have repeated dose and organ toxicity, neurotoxicity, and so on, right? So there is quite a lot of tests that we do before we can allow a compound on the market, or we say we don't allow it on the market. What I will focus on, and because that's actually a little bit my expertise, and therefore I have to make a little bit of a focus, is on mutagenicity and carcinogenicity, which is actually an endpoint that we do in humans, but we don't do that in ecological settings, right? So we hardly look for tumors in animals in ecological settings. So it's not really an endpoint there. So this is the actual scheme of risk assessment. That's all.
Like the human, the effect on human is not really to deal only with the animals. And maybe one thing which is important in what you say, the difference between environmental risk assessment and human risk assessment. I mean, the risk assessment in general is always linked with acceptance of the risk.
Yeah.
It's also very important because we are facing risk all along the day. When you're crossing the road or whatever, you say, okay, there is a car coming. Should I cross the road or not? So you have to accept the risk when you do that. And we accept way more risk for ecosystem that we accept for human.
Yeah.
For example, when you have proven effect that, for example, I don't know, one compound will maybe make some fish smaller. We don't like it, but still it could be acceptable. When if we have the same effect on human population, we will not accept it. So the acceptance of risk for ecological studies is higher than for human studies.
Yeah. So the first point you made is that when you do look for cancer in animals, you actually use it for human risk assessment, right? So you want to see whether a human living in that same environment may also be at risk for cancer because the animals living in that environment develop the cancer, right? So what you are then using actually is the animal, what we call it as a sentinel animal, right? Because we want to predict then what is going on in the animal in the humans. I will come back to that in a later stage. Okay, so this is the scheme of risk assessment. So we start off with hazard identification. I will talk about that in the first slide after this. Then we have dose response assessment because we want to know. So is a compound able to do something? This here is how potent is the compound in doing that. But of course, you need exposure assessment, which is 3, and then you combine these two and the exposure assessment to come up with so-called risk characterization. And this whole process here, this is what we call risk assessment. So as I said, I am a member of the Dutch Health Council doing hazard identification. I'm only involved in this first part. We don't do this down here. The next step would be risk management, right? So if you have that information, what do you do with it? Do you allow the compound on the market, but you have restrictions, or don't you allow that compound on the market? That's more the management, and I will not really dive into that today. But you might have to in your project, right? Because there you have to come up with ideas how to manage the risks. So let's start with step 1, hazard identification. I think it's a nice analogy is to look into shark, to look at sharks. A shark can kill you. You all know that, right? So the shark is a hazard. It is something that has the potential to harm you. But if you don't go swimming, right, the shark cannot touch you, so you're not exposed. So that would be the difference between hazard and risk, right? So if I go swimming and I have a hazardous shark in that water, then I am at risk, right? So that is a very important difference between a hazard identification and risk assessment. And actually, a lot of our work in risk assessment is based on hazard identification. Our safety, as we sit here, is based on hazard identification because a lot of compounds are identified as being hazardous and are not allowed on the market at all. So so you don't get exposed anyway, right? So the setup at this moment is, if we want to keep the population safe, that means that we have to identify those compounds that are able to damage the population or the individual, and if it is so, we skip those compounds, right? There are some differences there. There are some compounds that are allowed, but I will come back to that later, right? So hazard is the potency of a compound to damage. Risk is if you are exposed, right? So if you don't go swimming, you cannot be eaten by a shark, except if you live in Hollywood, because in Hollywood you have the Sharknado, they can fly. Who saw this movie? It's ridiculous, right? And they made Sharknado 1, 2, 3, 4, 5, 6. It's unbelievable. This is the second one, by the way, in New York. Okay, so what is the general principle of test strategies? So we want to test whether a compound in hazard assessment, we want to test whether a compound is able to damage our cells or damage our organisms or organs. So the first principle is that we have to try to obtain a maximum level of information using a minimum number of tests. Of course, you can do all kinds of tests. You can come up with a of tests, but that's not doable, right? Yesterday, somebody said there were over 1 million different compounds, and we are producing new compounds every day, right? If we have to do all those tests on all those chemicals, it's simply not doable. It's simply not, we cannot pay for that, right? So therefore, we have to come up with a limited number of tests that are actually giving us the most information. And I think that's also one of the things that we try to force you to do in making a selection of the chemicals that you could measure in the lakes here, right? Yesterday you discussed that with your group, right? You have to make a selection. You cannot simply choose all, right? So we need those tests that give the maximum information with the minimum amount of effort. Another principle, and I think that's one quite important and becoming more and more important over the years, is that we reduce the number of animals that we use, right? When we developed the whole system of risk assessment, actually we were less concerned about animal rights as we are now. So we had tests which really cost thousands of animals, right? So one test, thousands of animals. And I think that we cannot do that anymore. So we really need to refine our methods and actually make sure that we use less animals. And I think that's where I think also the new part comes in, because we have this, I'm now describing the old way of risk assessment. But in the new part, I think we are addressing more and more how we can reduce the amount of animals. Again, if a compound is mutagenic, or and there is a non-mutagenic substitute available, the compound is not allowed on the market, right? Only in some cases, compounds are allowed, but only if the benefits are greater than the risks, right? Think about chemotherapy, right? It's a clearly mutagenic compound, but it is allowed on the market because it's used for treatment of cancer, right? So this would be a very clear example of an exception. And so this is quite important. And to test the upper two, right? So obtaining the maximum amount of information without actually using a lot of animals, we have the OECD test guidelines. So these are, as you can see, you have the OECD guidelines. They all have a number. The OECD stands for Organization for Economic Cooperation and Development, and they organize more or less the whole risk assessment for all the compounds that we need. So they all have a number, and you can see these are in the 400s, right? So because I focus on those that are needed for genotoxicity and mutagenicity, right? So there are more, of course, and they have then a different number. Bojana yesterday, she already mentioned that we start off with looking in bacteria. So we have, for instance, bacterial reverse mutation test, the AIMS test. Ever heard of the AIMS test? Yeah, okay. But we can also go into mammalian cell gene mutation tests. And actually, we put more emphasis on the mammalian cells because, yeah, bacteria, they are not eukaryotes, right? So we use them as a screening tool, more or less. But I think more and more focus is coming on the in vitro mammalian gene mutation tests. And there are also quite some developments there. I think you all know about the new sequencing technologies. It's growing enormously, also in accuracy. So nowadays we can even see mutations already at a very low level using sequencing technologies. So I think that's the way, one of the ways forward. Then we also look at chromosomal mutations, and we look at, for instance, measuring DNA effects. Some of those assays are still acceptable. Others nowadays, they are downgraded, and they are no longer really accepted by the regulatory bodies, but they can be used as additional evidence. Like, for instance, the UDS, the unscheduled DNA synthesis. So what you actually do is you see whether there is DNA synthesis outside the normal cell cycle, right? And this is usually the DNA repair. If you have DNA repair, it also means that you have DNA damage. Otherwise, you would not have DNA repair, right? But this one is now downscaled. It's not so much important anymore because we also see that DNA repair is a good thing, right? So why would you use it if you're measuring a good thing? I put an arrow here at 474, an arrow here at 487, and an arrow here at 489, because this is the micronucleus test, this is the micronucleus test, and this is the COMET assay. And I think these three will be discussed later on this week and next week, right? I think Stefano is going to talk about micronuclei tomorrow, right? So then he will tell you a little bit more about these assays, how that works and what they tell us. Next week, we will have Sabine and Amaya here, and they will tell you about the COMET assay and how that works and what information that assay can actually give you, right? So I don't go into detail here. They will discuss those tests in more detail later on. So these are these test guidelines, and usually regulators really want tests that are done according to the guidelines, right? If you come up, if a company wants to get a drug approved and they don't do the let's say the test guideline tests, the compound will not be approved. But you can of course do tests without guidelines as additional information that is needed to get the compound on the market. And these tests without guidelines, they are also now growing in numbers because we are developing things like AOPs, which is adverse outcome pathways. Again, I will come back to that in later slides, right? So it's more and more that we are using non-test guidelines tests and put that into the weight of evidence to get a compound accepted. Yes.
The chemical itself.
Yeah. As I mentioned yesterday with the presentation of one of the, I don't remember who, but the regulators are very conservative, right? And this is, let's say, the conservative way. You have to do the test guidelines according to OECD, and this, let's say, is the more new developments, and it's not yet generally accepted. Right? They do allow it, but it's not yet generally accepted. At this moment, you really have to do this approach. Otherwise, you will not get it on the market. No, not necessarily, but they give you more information, I think. Right? So, but I will come back to that later on. Right? So you really, as I said, the regulators are very conservative, and maybe it's good that they are conservative, right? This whole system of risk assessment was set up in the previous century, and actually it was quite successful, right? As we sit here, we are quite safe because we know which compounds are bad and compounds are not on the market, etc. Sometimes there are mistakes, of course. Sometimes there are accidents. But overall, I think we are in a very safe world, right? And the regulators say, why change that condition, right? Never change a winning team, a coach would say, right? So if it is safe now, why do we change it? And then maybe we don't know in what direction it is going, right? So that's why they are so conservative. So I can understand their line of thinking. They are conservative, but I think in line with reducing, especially the number of animals and getting more information, also using new techniques like sequencing and so on, I think we need to move on from the traditional tests. But I think there's a big difference in the way of thinking between a scientist, and I think you are all scientists here, and a regulator, right? A regulator doesn't care. He just has to tick boxes, right? Well, it's maybe a little bit denigrating, but it's how it is, right? So they really just tick the boxes, and if the boxes are ticked, it's fine. Right? Is this an answer to your question? Okay. Okay, so that was hazard identification. So we do tests to see whether, in this case, to see whether a compound is able to induce mutations, whether a compound is able to induce chromosomal aberrations. And if so, then we don't allow that compound on the market. So you have the compound, you don't allow it, you are not exposed, there's no risk, right? You have the shark, if you don't go swimming, there's no risk. So in some cases, you allow a compound, and in some cases, because sometimes there is no substitute. And sometimes compounds are being used in the past, and now we see that they are dangerous, but now they are there, right? And then we can, of course, stop using them, but they're still there. And sometimes they can be very persistent, right? PCB, for instance, right? There were accidents in Italy and India decades ago, but we can still measure those compounds in our environment, right? So sometimes you have to deal with that in a different way, right? So that is then that is something that we have to go into exposure assessment. But now I would like to go into dose response. So we know that a compound has some potential to do something, to make somebody sick, but how well is it? What is the potency of that compound to do so? So then we have to go into dose response. How much of a compound do I need to get a certain effect, right? So because because in toxicology we all know the dose makes the poison, right? If I make the dose high enough, I will see something, right? So sometimes the doses can be that the danger can only be at extremely doses that we will never reach in real life, right? So then you could also say that compound might be usable anyway. And so dose responses are very important in the next step of risk assessment. So what you do is you take cells, for instance, if you go in vitro, or you take animals if you go in vivo, and then you expose the cells or the animals. This one is clearly in animals because it's milligrams per kg body weight. And then you look at the response, and the response can be anything that you would like to understand, right? So mutagenicity, carcinogenicity, you name it, right? And then you make a dose response, and you see that at a certain time, a certain dose, you will have a significant response in your outcome, for instance, mutagenicity, right? That point where the lowest dose that you test that is statistically significant, this is what we call the lower L, right? The lowest observed at first effective level, right? This is the NOAL. So that's the highest dose. So this is the lowest dose that is still significant. The NOAL is the highest dose that is not significant. No effect, exactly, right? You might see an increase, but it's not statistically significant, right? So this is the NOAA. But we can, of course, the MTD, by the way, is the maximal tolerated dose, right? That is where you say, if I give an animal this amount of the compound, nothing will happen to the animal, right? Except carcinogenicity, because that we don't test in MTDs, right? Well, we give an animal and we look for the dose that is maximal reachable for those to not doing anything with the animal. So we have this effect, low observed effective dose, NOAA, and these can be used for regulators, right? Because then we know what the lowest dose is that it still makes a statistically significant effect. How do you feel about NOAA and LOAL? What would be the problem here? Yes?
Problem with substances that don't behave like in a linear fashion, like for example, nanomaterials, they're more reactive like in lower concentration when they're not as clumped together compared to higher concentration. So something like that might be like difficult to assess.
Okay, yeah. But if you're talking about particles clumping together or not clumping together, then it's much more on a problem with the dosing, right? It's not maybe the effect, okay?
There are still some people that will have mutagenic effects at that doses.
Okay.
I don't.
Yeah, that's a good point. I will come back to that later on with uncertainty factors. Yeah. Okay. Yeah. That's why we do acute tests and chronic exposures. I will also come back to that. Good point. The long exposure. Yeah. So this would be you could have here a cumulative dose, right? So you have multiple exposures. For mutagenicity, we usually expose 28 days in a row, and then we sacrifice the animals 3 days later, right? So this is a general, but you can also expose longer. I don't know, right? What if? So this is the lowest dose that was tested and statistically significant. What if this point here was the lowest dose that we tested? Would that then be your lower L? We didn't test lower, right? We did a dose finding study. We came up with some doses. We tested those, and then this one is statistically significant. Right? So let's say this is the lower L, right, in this figure. But maybe if I go from 2 to 1.75 up there, maybe that's also still significant, or not. Right? You don't know. Right? So lower L and lower L are actually very dependent on your study design, the doses that you choose. And so if I choose a dose which is statistically significant, and I have a dose, let's say 1 order of magnitude lower, which is not significantly increasing the mutagenicity, for instance, you don't know what happens in between, right? And that is a problem, because that can be quite some difference over the whole run, right? So if you were talking about overall exposure, cumulative exposure, a small difference in an acute dose can already make a big difference in chronic exposures, right? So there is some problems with lower L and lower L, although they do, of course, give you information. But the doses that you choose is very important because that can affect your outcome. And we do have to make choices in the doses. We cannot give a continuous scale, or we cannot make multiple groups in between, because that would take too much animals. You can do that in vitro maybe, but that's too much work. You can definitely not do that in animals. Or you have to reduce the number of animals in each group, and then you don't reach statistical significance. Right? So there is the study design here is making a problem. So therefore, there are new developments in dose responses, and that is the benchmark dose response. So what you actually do, you see actually something similar as here. You have a response on the y-axis and a dose on the x-axis, and you do have you choose some doses in those animals. And then instead of determining the lowest dose that is statistically significant or the highest dose that is not significant, you actually plot a line, or you estimate a line, the best fitting curve through the points that you have, right? So you assume that there is some, that you assume that the line between this point and this point is logical in the whole figure, right? It doesn't go like this, right? So there's no hump there, right? So you can expect that this line will fit the real effective dose response. And then if you say, okay, this is my background, right? So this is the amount of mutations or the amount of dead animals or whatever endpoint you use in the control group. And then you say, okay, I accept a certain critical effect size, which is here. So for instance, I do an increase in 50%. That is what I allow, 50% above the background. And then you can look at the point where you have that dose, right? So that would be your what we call point of departure, right? So that is where we start off calculating how much we allow for humans, right? The advantage of this is as well that if you draw this line and you have all those points, which is actually formed by a number of animals, so you have a standard deviation around each point, is that you can also have some confidence intervals around the line, which can lead to, let's say, the lower level of the confidence and the highest level within a certain confidence interval, right? So it also takes into account the uncertainty that we have. Whereas with lower L and lower L, we don't have that, right? We don't have any uncertainty in there. Here, if the difference between the BMDL and the BMDU, so the upper and the lower limit, is very large, you know that the assay was really not really reliable, or the estimate of your benchmark dose is not really reliable because there is a large uncertainty around it. And so this is, I think, a very nice example of how we improved over the years by going from lower L into benchmark dose analysis. Yes.
You see the difference with the lower L and the BMD, but I think it's still dependent on which dose you choose for your experiment.
Yes, of course, because if you would not do this one and this one, the line would go, or if you would not choose those two lower ones, for instance, your line might go up earlier, right? So indeed, it is still dependent on the doses that you choose, but it's less strongly dependent on your choices as compared to these, right? So it also makes, it is also important thus to make use of a large variety of doses, but by determining the lower L and lower L, you really have to narrow down to the point where you cannot detect anything anymore, right? Whereas here, if you just make a spread of your exposures, you will be able to draw that line, right? So you're right. It is dependent on the choices that you make, of course, but it's definitely less affected by your choices as compared to the left side.
That's right.
Yes.
The best fitting curve. I didn't understand the whole.
No, so the you make one curve, which is the red one, right? And the other ones are actually what's it called, the confidence intervals all around that line. Yeah. Confidence interval. So because you have a fitting line, because there is variation within your points, you always have the possibility that your line is maybe a little bit higher or should be a little bit lower, and that's your confidence interval. So for instance, your 95% confidence interval around this point here, And then you can, and that's also why we can come up with the benchmark dose at the lowest point, which is actually the upper line of your confidence. So this would be one of the lines within your the upper line within your 95% confidence interval, and this one is based on the line at the lowest side of your confidence interval. Yeah, most of the data will be in this one. So this is the most probable one, right? So it's like the bell-shaped curve that we discussed yesterday, right? So most of the data will fit this line here, and that's why that's the one that we choose. Okay, is that a little bit clear? Yeah. More questions? Yeah.
Why do you have that many lines? I understand the confidence interval, but
yeah, but you can of course choose different confidence intervals, 95, 90%, yeah, these kind of things. Yeah. And you can also, of course, and that's making it a little bit more complex, is that you can, of course, choose a different type of fit, right? And then you choose the best one, I would say. If you would like to play around with this, there are programs freely available on the internet. If you go to the Dutch website, the Dutch governmental website of the RIVM, it's the Dutch Institute for Safety of the Environment. They have a program on their website called PROAST, P-R-O-A-S-T, not Prost like Prost, but PROAST, right? And there you can fill in your data, and then it will come up with this fit and your benchmark dose, etc. Right? So because you can also use that for all kinds of endpoints, right? So if you have a certain dose, you could actually use that for all kinds of endpoints, like gene expression endpoints, like mutation endpoints, cell survival, etc. Right? So you could use this approach quite extensively. Yes. Sorry. Yes. I didn't mention it here, but that's not in this from this one here. So if you would have in your response, you would have animal death, then your lethal dose, the LD50, can also be calculated like that. Yes. Or if you talk about cells and you have a concentration, it's the LC50. That's the lethal concentration, where 50% of your cells die. Right. Well, we never use the LC50. I don't see the use of it, because when we do experiments in Maastricht, we always expose cells to viabilities of at least 80%. When we kill them, we say, okay, then the dose is too high, right? Is somebody working with LC50 or LD50 in this audience? You heard about LD50 and LC50. Okay, that's good enough. Okay, so when we now want to then say something about the slope, right? So when I go back here, we actually don't know. When we go to very low doses, we don't know whether it is going like this. So do we have a threshold, yes or no? Or maybe it's going like this, right? So if 10 would be your detection limit, so you don't know how the line progresses on the detection limit, right? So that is actually a problem, and that is also affecting cancer risk, because if we assume a slope like this, for instance, you assume, so if this is the dose of a compound, so you expose the compound to an animal to a compound, if that would be the dose here, and that would be, let's say, the amount of animals with cancer, and you would draw a line like this, you actually assume that there is a threshold. But we don't know that, right? Because usually cancer endpoints are done with animal sizes of, let's say, 50 animals. And then you don't see an increase above the background, so in unexposed animals. And then you might always say that maybe you see a small increase if you use 500 animals or 1,000 animals. right? But we don't want to go that high in the animal count. And so whether there is a threshold, we don't know. And we actually don't know how to extrapolate under the level that we cannot detect anymore or cannot see anymore. So what we then often do in risk assessment is we do a linear extrapolation through the zero, right? We do not assume a threshold. And then if this would be the lowest dose that could be tested or still be detected, and we don't know how the slope is going underneath, we simply go, we make a straight line. How do you feel about that? What will be the consequence of this using a straight line? The model is not completely correct. Yes. The straight line might not be correct, right? If we take the straight line, if the line would go like this, right? I now force you to make a choice. You said over or estimate. I want to force you to make a choice. If we make a straight line, do we overestimate or underestimate?
Where they touch together.
Yeah.
They're really defining point. Under it is you're underestimating your effect, and over it you're overestimating.
Yeah. So this is the line that the regulators use, right? And this is the line that the scientists think is the real line, because we do think nowadays that there is a threshold for carcinogens. This line here is actually considering one single molecule. You are exposed to one single molecule of that compound, reaching your DNA, making a mutation, and that mutation leads to cancer. Right? That would be this straight line through the zero. Right? We don't believe in that anymore, right? Because we know cancer is an accumulation of mutations. We have protective mechanisms like detoxification, etc. We do think that there is some kind of a threshold. But regulators, as I said, they are conservative, and they say, we take the straight line because the straight line is more conservative, right? If we want to predict cancer outcome, and we take the line that we as scientists think is the correct one, right? If you would say, I accept one cancer case in a million, that would be down here. Then the dose that I can accept with the red line is actually higher than the dose that I would accept with the more conservative approach. And that's the approach that the regulators use, because this is more conservative, leading to a better protection of the environment or the humans. But of course, it also can have consequences, because if a compound actually falls over a compound that is already there in the environment, if that compound actually you need to clean up or something like that, or you need to take measures, that means that you have a lot of effort to make sure that the exposure is low, right? So this can have serious consequences. Okay, now then a little bit about the differences in compounds. Right, so we have the different. What time is it? I'm 1 hour now already. So we have regulatory requirements, and they actually depend on the amount or the type of compound that you use. Right, so for industrial chemicals, we have REACH, right? But we also have other rules for pesticides, pharmaceuticals, and cosmetics. So for cosmetics, for instance, we only rely on, or we have to rely on, in vitro experiments, because for cosmetics, animal experiments are completely banned. At least in the Netherlands. I don't know whether it's all over Europe, but in the Netherlands, it's completely banned. For industrial chemicals, we are dealing with REACH, right? So that's a strategy based on genotoxic potential of chemicals. But there are also, of course, non-genotoxic substances. And with regard to mutation and cancer outcomes, these compounds, if they are not genotoxic in our in vitro models and in animals, then we say, okay, they are not genotoxic, they are not mutagenic, they are not carcinogenic. We allow them on the market. And we only test them for carcinogenicity if there is a reason for it. For instance, it is a widespread use or long-term or frequent exposures. So then you think, okay, maybe humans are exposed to that compound quite a lot, so let's test anyway, right? For pharmaceuticals and pesticides, we are required anyway to do a carcinogenicity study in 2 species, rats and mice, for instance. We are really required to do that just to keep safety up to date. And these cancers, so for these pesticides and these pharmaceuticals, these carcinogenicity assays, so is a compound able to induce cancer? These are actually very long and expensive experiments. These are 2-year chronic exposures, right? But they are very effective because it has been proven that they can detect, this assay can detect genotoxic, but also non-genotoxic carcinogens, right? So together then with these compounds, so this assay will give you hazard identification. So is a compound able to induce cancer? And it also can give you some kind of potency information. So how much of the compound do you need to induce the cancer? Disadvantages is that you use a large number of animals, right? So 500 animals per species per compound. It's enormous, right? But again, we are required to test. It's what the regulators want us to do. It's time and labor intensive. The relevance for humans might still be questionable because we are measuring in animals, and there's limited insight into mechanisms. And exactly there is, I think, where we can improve, right? So if we want to reduce the number of animals, I think if we get more insight in the underlying mechanisms, then we can actually say, okay, this compound is harmful and this compound is not. Right? So alternatives are urgently needed, and that's now in progress already for some decades. Then we had hazard identification. We looked into dose response assessment, and now I'm going to exposure assessment. Right? So we want to assess exposures. So I want you to take a piece of paper and make a list of 3 compounds which you think are, for you, the most dangerous ones in your daily life, which we really have to measure and make sure that we are not exposed to those in real life. Make a list, just 3. It's a little bit personal, right? So what is your concern? Which compounds do you think are important to assess? So now we are going into chemicals that you are exposed to that are on the market, or exposure cannot be avoided, right? Like diesel exhaust, what else? Wood burning in a fire, etc. So they are on the market and you are exposed. They should not have been released, but because it was before that time, they are still around. Okay, let me just choose a few of you. Francesca. You don't know. You have no clue. Okay. Yeah, you have 3, or at least your top.
I would say persistent organic pollutants.
Persistent organic pollutants. Yeah, yeah. It's also on your list, right? For your assignment.
Yeah.
Yeah. Why is that one on your top list?
They have compounds that are really difficult to degrade, so they can stay for really long times in the environment. Or
yeah. So now we ban them, but they are still around, and they will be around for the next decades, right?
Yeah.
That's your top.
Well, the one thing I thought about in everyday life is barbecue.
The
What
PAHs.
barbecue is a lot of PAH
Yeah.
or polycyclic aromatic hydrocarbons. Now, the thing that I know is when they are analyzed, they are usually analyzing groups. So
Yes.
I think it would be better to get some new methods to analyze a single PAH.
Okay.
Because you said to think about something that we think should need more attention.
Yeah. Yeah.
And some of those PAH are also persistent organic pollutants. So we would cover that.
And they are all around the place, right? Actually, they have been detected in star systems because they give a very specific spectrum, and that has been detected in star systems. It's really intriguing. But we are exposed to PAHs all the time. Barbecue is just one example. The diesel exhaust, right? So when you came here in your bus and you was waiting for the bus and the cars pass by, you inhale them, right? So you are exposed to those all the time. And so the WHO came up with 10 examples of compounds that may be of concern. I think lead, especially in the Netherlands, lead is still an issue because in the past we had water plumbing in lead pipes, and we replaced all of them. But in a lot of old houses, I don't want to scare you if you go to Amsterdam, but especially in Amsterdam, old houses, they all still have lead plumbing. So if you live there, you are exposed to increased levels of lead, right? So you have a lot of, as you can see, metals like mercury, arsenic, cadmium, but also asbestos is there, right? So there's asbestos. It's also quite concerning. And air pollution, which includes also your PAHs, right? So there is quite some concerns. But indeed, there are also some new emerging concerns like the PFAS. Who heard about PFAS? Yeah. Or the nanoplastics. In the Netherlands now, it's also quite a concern is wood smoke because of the high prices of gas and energy prices. People switch to burning wood for heating their houses, which may lead to new types of exposures and new types of risks. Right. So exposure, what I want to, the point that I would like to raise here is exposure cannot always be avoided, right? So of course, new chemicals, we can make sure that they are not released on the market, but some compounds, you're simply exposed. You cannot avoid it. And then it's important to know how much you are exposed and whether we can take measures to reduce the exposure in any way, right? So that is where we come up with exposure assessment. And exposure assessment can be done in different ways. It depends on where the chemical is present. Is it in the air? Is it in the soil? Is it maybe in the water, the groundwater or surface water? Or is it maybe in the plants, etc. Right? So it's at different levels. And that also determines how, as humans or animals, we are exposed to those compounds. If they are in the air, we are exposed to them via inhalation. A fish, for instance, if you have air pollution, a fish is only exposed if somehow that compound is dissolved in the water or precipitates into the water, right? Because the fish, they don't breathe air. They are in the water, right? If it is in the soil or in your plants, you ingest them or you have dermal exposure. For the general population, actually, dermal exposure is not so important, but it's a lot in workers, for instance. Then dermal exposure may be really relevant, right? So you have all kinds of exposures and you have all kinds of exposure routes, right? And you can measure compounds in all those environments and all those situations. I want to go back. So what you actually have is, this is when you measure it in the environment, this is what we call external exposure, right? So if you have a human being and he is exposed to the air, we can measure the compound in the air. This is external exposure. That does not mean that we know how much of that exposure reaches the inside of your body. That would be internal exposure, right? So external exposure is easy because you measure it on site. Internal exposure is much more difficult. Of course, when you deal with animals, you can catch an animal and you can analyze any tissue of that animal if you sacrifice it, right? If you don't want to sacrifice it, you can take blood and then put the animal back, right? In humans, we have multiple options, but of course, if we are dealing with healthy individuals, because we are exposed as healthy individuals, and I want to understand how much you are exposed by measuring inside of you, and then, for instance, if you are exposed via inhalation, I might say, inhalation, the first organ to reach is lung. I want a piece of lung of you, right? Because I then want to assess the amount of compound that reaches your lungs. Would you agree? No, of course not, right? So we rely in humans, if we want to do the internal dose, we have to rely on what is doable in humans. So what can we reach non-invasively and would people would allow, right? So what I would like to do is I have a whiteboard over there. I draw very quickly BioBob. I call that guy BioBob, right? I draw it on the screen, or on the board, and then I want you to brainstorm what tissues or what samples can we take from humans, non-invasively, which is also, I think, also nice for you, for your future studies, not only for risk assessment. So what type of tissue can we actually measure, right? So I draw BioBob, and by the way, it's not only BioBob, it's two persons in one. It's also BioBabette, so it's male and female together, right? Meet BioBob, right? BioBabette. So on this side it's BioBabette, right? If you want to collect samples from that individual, what could you take?
Dermal tissue.
Dermal tissue. Dermal tissue? How do you take dermal tissue? Not invasively. So scrapings. Okay. Dermal. Let's take it from the arm. Okay. What else? Urine. What else? Saliva. Hair. Nails.
I would go for buccal cells.
Buccal cells. Good. So saliva / buccal. Right. So the difference here is saliva is a liquid, right? So you can measure compounds in the liquid. The buccal cells, or with double C, I guess, right? So buccal cells, you are looking at cells, right? So the micronuclear assay can be really well done in buccal cells, which can give you also additional information, right? So that's good choice. Yes, more. Air, yes. So exhaled air, right? Actually, there is a lot of information in exhaled air. Right? We do exhaled air analysis in Maastricht, and there are thousands of compounds in there, which you can also use for diagnosis of diseases and so on. Yeah. More. Feces, yes. I'll put it here with the feces is also quite interesting, right? Because we use features, especially in Maastricht, for people from IPD patients, for instance. You said blood? Did you say blood? No? Oh, okay.
Yes.
I would say
Blood is invasive.
Blood is invasive, really? Officially, yes, officially, because you have to go through that arm, right? But let's say blood is acceptable because it's a routine analysis, right? So we take blood, right?
Yeah.
And blood, you can, of course, you can take serum or plasma, or you take the cells, right?
So we can do a lot of types of these swipes.
Swipe.
Nose, tongue, ear.
So nose,
Ear.
ear,
Yeah, we can skin.
skin. So nose, ear, skin.
Swab is the.
Swab.
the
Swipe.
is the word, swipe.
Swaps with B, right?
Yes, the.
Okay, you know what I mean.
And go for breast milk.
Breast milk, yes, because it's also Babette, right? Breast milk. What else?
Semen.
Semen.
Sweat.
Sorry?
Sweat.
Sweat. An armpit. Okay, more on.
If it's about it, then placenta.
Placenta. Yes, I like that one. I actually do a lot of work on placenta because it's non-invasive, right? And for research purposes, it's all you can get it without ethical approval, at least in the Netherlands, because it's considered waste, right? But the placenta is quite interesting. Yeah.
Yes.
Tears. Ah, we make her.
That's emotional.
Yeah. Okay. We had a summer school within Comet. It's also a European project in which we did Comet assay on not really tears, but cells from the eye. Right. So you take a little bit of cells from the eye. So it was not that pleasant, I would have to say. It's not invasive, but it was not that pleasant anymore. More. Are we done? You can see we can have a lot of measurements, right? Internal measurements. And then, of course, what you need to know is if I measure something in milk, if I measure something in blood, right? That means I have been exposed to that compound. Otherwise, it would not be there, right? So I think measuring all kinds of these samples would be very interesting. And your choice of the biomarker you would like to use also depends on your endpoint. If you want to measure a chemical, you would like to have maybe fluids, right? If you measure, for instance, DNA damage, you need cells. And if you then, for instance, you talk about inhalatory exposure. Oh, we missed one. Inhalatory exposure, you can, of course, take UCO. But how do we get cells from the lungs? What we used before is sputum, right? You can ask people to cough up sputum, and then you can take cells of them, right? So there are all kinds of ways, depending on your type of exposure and your endpoint, you can choose the biomarker that you want, right? And I think that's something you can think about. This is in humans, but you could also think about in your project. For instance, if we take a fish, where do you want to measure in the blood? Or do you want to measure somewhere else, right? Or do you want to measure in an organ of that fish? If you take a plant, do you take the tip or do you take the roots, right? That's all kinds of things you have to consider in the measurements that you do. And I would really like to urge you to think about that, right? I'm not giving you any answers at this moment, but if you are doing your assignment, I would say think about not only simple, okay, we take a plant, but then also what part of the plant? Do we take the roots? Do we take the leaves? Whatever, right? Think about that. So what would be the advantages of biomarkers? I switch on this one again. What would be the advantages of biomarkers? It is an integration of time, I would say, right? So if you would measure air quality, I measure it today, and then maybe if the wind comes, tomorrow the wind turns, and we have a different type of exposure, right? So if I would measure tomorrow, I have a different outcome. Whereas the animals, they are actually exposed for a longer period of time, and the damage accumulates or the compound accumulates in the body, right? So we have a thing called bioaccumulation, right? So that certain compounds accumulate in fish, and therefore it might be easier to measure in time, right? So you integrate a longer period of time in exposure, and you don't have the fluctuations anymore that you have in environmental exposures, right? So this is quite an important issue. You are measuring actually the dose that reaches the target, right? So external exposure does not mean that this is actually the compound, the amount that you are reaching. Better linked to animal models. and it's also, as I said, it can take into account bioaccumulation. Oh boy, I have to hurry up. I'm at the last part. So we have risk characterization, which is actually the combination between what we have here on this side. So a compound is potent, and we have a compound can do something, and we know how potent it is. We have the exposure assessment, so we know how much we are exposed to that compound, and we actually have then the risk characterization. The risk characterization is nothing more, very simply said, that we have the hazard, so we know what the compound can do and how potent it is, and we multiply that with the exposure. So do we exceed the exposure that we have? Do we exceed the amount that we need to have a biological effect, right? So you more or less integrate exposure data with dose response data to obtain risk estimates, right? So it gives especially risk managers information about what to do, right? So should we deal with that compound, yes or no? So there are quantitative aspects, but also qualitative components in that analysis. And it is also important that we also have to identify uncertainties and data gaps, right? So it's not only that we say, okay, we know everything, right? But we always say that, okay, with a certain degree of, with a degree of certainty, we can say that this is a dangerous compound and you should not exceed this amount of exposure. And so this is quite important. As I said, we are doing this, there is some uncertainty there, right? Because we are doing most of the exposures, if we talk about human risk assessment, we're doing all those exposures in animals, in mice and rats, but we are not mice and rats, right? We are bigger. This is one of the differences, right? So, but there are many more, right? So there is, what we then do is, because we want to deal with these uncertainties, we take the dose that is safe in the animals, right? Or what we consider this point of departure. And then we divide the dose that we allow to exposure. We divide that by all kinds of uncertainty factors, because we say, okay, we are not certain about that. How can we have to extrapolate from mouse to human. So we don't know how much that is. So therefore we built in an uncertainty factor. So we have an exposure, a dose that we detect in animals, and then we divide that dose by the uncertainty factor between animals and humans. Another one is short-term versus long-term exposures, right? So we often in animal studies, we do short-term exposures, but yeah, we are often exposed over a long period of time. Maybe that is more dangerous than a short-term exposure. So therefore we have uncertainty factors there. We have uncertainty factors for database insufficiency. If we are not really sure about the data, then we add additional uncertainty factors just to be sure. We have, and I think this is very different between environmental and human exposure, right? So we want to protect even the most sensitive human. And that's why we also have uncertainty factors to protect the most sensitive human in our population. And that's what Bertrand said in the beginning. We don't do that for animals, right? We care about the species and not about the individual. And if we kill the most susceptible ones, so what, right? Because the species will be there next year as well, right? So we allow more. So if you have data on long-term exposure, like 2 years, it's almost the whole life of that animal, then you do not use that uncertainty factor, right? So these uncertainty factors are only used if you really need them, right? If you have uncertainty about that situation, right? I think the animal-human uncertainty factor, that's the most important one. Bertrand.
See, as well, depending on the compounds. For example, there is a specific one for the pesticides to protect the ecosystem from the pesticides. In that case, we use for environmental risk assessment, we use uncertainty factor as well. So there's 2 types. One for the acute risk. In that case, we use LC, still the LC50. Like okay. This. But we divide it by 100 as an uncertainty factor. And for chronic risk, we use the lower values. Oh, actually, no, yeah, the lower values. In that case, we divide it by 10.
Okay.
As a sensitivity factor to protect that. And once again, when we use on animal species, usually we try to use sensitive species. So based on the fact that if we are able to protect this one, we will protect most of the ecosystem. If this one are not impacted. So
yes, so in ecological studies, you still use LD50 because animal death is one of your endpoints, right?
Yeah.
Whereas in humans, we don't use LD50. Hopefully. Okay. That brings you to the last part of my presentation, which is the norms. Who has heard about norms? Victor? Bertrand, you heard about them? Okay. NAMs means new approach methodologies. Right? Some people also say it's you should call it no animal methodologies, but I think that's not the correct word because even NAMs can allow some animal studies. But a lot of work on NAMs, new approaches, is being done in vitro, and we want to improve in vitro methods also to have a better prediction what is going on in vivo. Right. Yesterday, you had a wonderful talk of Bojana, right? She talked about the 3D models. I think that's a very nice example of a new approach methodology because the regulators, they really don't see that as something that there's no guideline for 3D models, right? But I think that could be something that comes in the future, right? So the norms are really something that is new, not generally. I think we as scientists, we think these are valuable additions to the regulatory, the regular testing strategies, but the regulators, well, as I said, more conservative. They don't want to change a winning team, so therefore they do not necessarily accept only norms, right? So they still want these OECD guidelines, and they accept norms as additional evidence. So there is a EU project, EPAA, it's the European Partnership for Alternative Approaches to Animal Testing, and the project goal is actually to develop mechanism-based approaches to predict, as in this case, carcinogenic potential of organochemicals. And so we want to get rid of animals, and therefore we go much more into mechanism-based approaches. Also to make better predictions of whether a compound can induce cancer, yes or no. And this mechanism-based approach is actually using the mode of action. It's an MOA, right? And in that mode of action, we have certain key events. We call them KE. Right, so, and then I will show you a moment. So this is what we then call an AOP, an adverse outcome pathway, in which we start with a molecular event leading to certain key events, and that leads to the disease at the end. And then you can, if we know the pathway that a certain disease, in which a certain disease develops, a certain outcome develops, then we can actually make measurements all along that pathway to show whether a pathway is switched on or switched off, more or less. Right, so the appropriate norms, what they want to do is, of course, we want them OECD approved, but you can think about all kinds of assays like in silico, right? We had models, as we discussed yesterday. We have in vitro short-term exposures or in vitro experiments, like Bojana told you, improved in vitro models, but also short-term in vivo models. So this is what we call then such an adverse outcome pathway. We have a molecular initiating event, right? And that leads to certain key events. And you can actually calculate, if you go to quantitative outcome pathways, that you can predict, if I have a molecular event, what is the chance of having key event 1? What is then the chance of having the key event 2? And so on, to end up with your adverse outcome pathway. So in this way, we think that if we add in more and more information in that pathway, we may be able to predict the outcome, the adverse outcome, in a much better way as we do right now. right? And so you can think about molecular endpoints, but also more on the tissue level, organ level. But then also this could be quite interesting approach also for ecotoxicology, because we can also look at the organism and the population. So what we actually would like to do, I wrote down carcinogenicity down here, but you can also think about other endpoints. So we have a mechanism-based approach to cancer risk assessment or disease risk assessment. So we have our in vitro models, improved in vitro models, in silico models. So to cover all those modes of action, we want to see whether compounds are able to activate and how well they are able to activate these modes of action. And we have our in vivo short-term studies, and then maybe together they can make a better prediction as we have right now. This is what such a filled-in AOP would look like. I don't go into detail, but what you can see, it's also cross-organ, right? So you go from a liver to a thyroid, and that interacts also with your endocrine system, right? And then you have your outcomes right here. So these could be outcomes. This is the pathway in which actually non-genotoxic carcinogens can elicit cancer without damaging your DNA, right? So these are most of the time missed at this point, because we focus with regard to carcinogenicity and mutagenicity, we focus often on DNA damage and mutations, but non-genotoxic carcinogens actually induce cancer without inducing those outcomes. So there were a lot of tumors that have an unidentified mode of action. Right? So we do not know how compounds induce these type of tumors. And then with using these modes of action, also the adverse outcome pathways, the AOPs, now we are able to understand why some of the compounds induce certain types of cancers. Right? So it detects also non-mutagenic carcinogens, and I think this is a concept of a mechanism-based approach, and it's really gaining ground. A lot of institutes are pushing this idea also to get it much more recognized by regulators. So what we would like to do with this approach is know the unknowns. Right? So we want to understand the modes of action. So therefore we can add that to the weight of evidence that we have. So if we have a limited test of OECD accepted guidelines, and then add that additional evidence to the portfolio more or less, then the regulators may accept the outcome or the compound much better, if we show it's safe, of course. I have a few slides on how to extrapolate from animals to humans, but I think I'm running out of time. And I noticed that these slides actually they overlapped quite a lot with the work that Bojana yesterday presented. So therefore, I will go through that quite quickly. I think this slide is quite interesting because it integrates the work that was presented by Bojana and also the modeling person yesterday. Right? So we use modeling, PBPK modeling, for instance, in which you look at how certain compounds distribute over the body, what are the doses reached in organs, and what effects do we then expect in all kinds of organ systems, taking into account dose, time, distribution, metabolism, excretion, all these kinds of things. And so this would definitely improve. This is the idea of the more complex cell systems. I think Bojana yesterday mentioned the spheroids, right, or 3D organ structures. We at Maastricht University, we often use co-cultures in which we culture actually multiple cell types together, for instance, an epithelial cell together with an inflammatory cell to see whether there are differences there, right? So there are quite some developments there to improve the models. And then, of course, I think this is also quite intriguing development, which is the organ on a chip. And quite interesting is that you can also connect organs, right? So a lot of compounds actually need activation or detoxification in the liver. So, and then they exert their effects in other organs, right? You can mimic that actually on a chip because you pump around all kinds of liquids, and then you can make such, so the liquid can go through a liver, artificial liver, of course, and then be exposing other cell types. Here, this is a nice a model in which you have the airflow here and your blood flow on the below here, and you can actually also, with the vacuum, you can actually also mimic the movement of the vessels, etc. Right? So there are a lot of developments that I think is quite interesting. I'm almost there. One of the last slides. Animal models. You can also think about, we use often mice and rats, but that might not necessarily be the best animal model. If we think about inflammatory responses, animals have, mice and rats have an inflammatory response, just like us, but the immune system of a mouse is different. We have to realize is different from that from a human being. If we, for instance, look at the composition of the blood, we have about 75% granulocytes as humans. Rats don't have granulocytes at all, right? So they only have granulocytes in their circulation if they have a serious inflammation somewhere going on, right? So that means that there are differences between animals, and there is now also some work going on in finding the best model based on basis of the genetic makeup of those animals, right? So for instance, if you would study this receptor, maybe then the pig is a better model for humans than the mouse or a rat. Whereas if you go for this receptor, then the rat is a good model, right? So there is some evidence there. The guinea pig, for instance, for this transporter here, right? So maybe you should choose your animal model better to have better outcomes. But I think we can also turn that around because we have a lot of evidence about compounds in humans before they are released and when we are measuring them, and maybe we can use them also for our animals in ecological studies, right? So that's why I added this slide. So it's not only that we can make predictions from humans, from animals that we use in our testing to humans, and we can improve that, but it's also the other way around. Maybe we can use information that we have collected in humans and can use that in ecological systems. So that brings me to the final slide. Hazard identification, risk assessment is a combination of all kinds of activities, exposure assessment, and I think for your project that you are doing this 2 weeks, I think you have to take all of these into account in the advices that you will give.